translate, and Alberto will also run a Spanish version of this workshop in the coming days. So this will be in English. Unfortunately, I don't know Spanish, but I can still answer any questions with translation of the questions. Alberto and I are both Qiskit advocates, and we bring to you the Qiskit Fall Fest Hackathon happening in a couple of days. So in this workshop, what we want to do is teach you the basics of quantum computing and those concepts, the applications of quantum computing. You get an idea of how quantum computing applications will affect us in the future, and also opportunities that you can use to learn quantum computing. There will be other workshops throughout the week. So I hope this is a good introduction to it. So to introduce myself, I am a computer science PhD student at Oxford in the quantum group. And Alberto, you can introduce yourself.
Okay, hello everyone, I'm Alberto. I'm a computer science PhD student from the Centro de Investigación en Computación from the Instituto Politécnico Nacional in Mexico.
So first of all, we'll just share, Alberto and I are part of an initiative called Quantum Universal Education. So it's not for profit, and we just run events, free events and materials that people can use to learn quantum computing, no matter their background or location or age. So anyone who contributes to helping make these resources can get a free t-shirt. And we are also sponsoring a prize at the hackathon that's called the Best Education Hack. Alberto just showed the t-shirt design on his screen, and it's also shown on this slides, the color options. So if you make an education-related hack, so something that can help people learn quantum science, quantum concepts, quantum computing, then you will be eligible for this category prize of prizes, and each member of your team will get a free t-shirt mailed to you. To introduce our community, Quantum Universal Education is mainly on Discord, so it's about 1,200 members on our Discord server, and we also can be followed on Facebook, LinkedIn, Twitter, and have a YouTube channel. And we do various events in addition to the educational resources. So we have a journal club that we hope to start again soon, and we did an anniversary celebration with many talks all from around the world. And we are also running a workshop this week at the IEEE Quantum Week conference. It's a quantum education workshop with a dozen talks that are from educators, quantum education researchers, and community leaders. I guess we'll start with the introduction to what is quantum computing first. In this slide, it's called Beyond Classical Computing because we want to get an idea of, well, how do quantum computers compare to classical computers in the coming years? In the bottom left, you can see the green area says systems today, and this means that in today's quantum computer, today quantum computers are still not very not very powerful in that they have a lot of error. So it happens that classical computers, meaning computers like your cell phone, your laptop, these things, those computers happen to naturally error correct themselves. However, quantum computers today, because instead of each bit value having either 0 or 1, they can be other values as well. Therefore, quantum computers have a lot of other error and noise that has to be suppressed. So in the coming years, not only does the number of qubits that we have in every quantum computer is expected to increase exponentially over time, but we also expect the probability that the gates will have error to decrease exponentially. To decrease also. So if you see that number of qubits is the y-axis, the vertical axis, and the probability of gate error is the x-axis. So you can see in the bottom left is systems today, which is green, but this blue dashed line right here, this blue dashed line represents what we can, the kinds of computation that classical computers can do today. So this is what, if a classical computer were to simulate quantum computers, this regime would be where the simulation could be successful. It's predicted that in the coming years, we're going to have quantum computers be able to access beyond this dashed line. So the first area would be quantum supremacy, this purple area. And these are the experiments, for example, if you hear from Google has done experiments that they believed to be, would take years to simulate on a classical computer that took them seconds to do on a quantum computer. So this kind of near-term quantum advantage, so experiment, is being done in present few years. Whereas in the future, it's predicted that quantum computers will be able to do more problems. In the near term, this is VQE, is variational quantum eigensolver, which is predicted to be one of the most natural uses of a quantum computer, used to simulate nature, which follows the laws of quantum physics. In the farther future, you can see over here, it says the green area up here is Shor, the fault-tolerant implementation of Shor's quantum computing algorithm. And we'll have a later workshop this week about Shor's algorithm. We can also think about how we can draw an analogy from classical computers when they first started to quantum computers today. On the leftmost column, about in the 1950s, so before most, if not all of us, were born, a very different time. In the 1950s, the computers back then they had algorithms that they believed computers could do, and then what they actually had in hardware was a bunch of vacuum tubes and just very simple assembly language, which is like programming in zeros and ones. Today's computers are much more complicated, and those algorithms that people dreamed about that could be run that they hoped could be run in the 1950s can now be run, and there's all these layers in the middle of how an algorithm can be compiled and run on hardware. And on the right-hand most column, this is an idea of how quantum computers are structured today. So we have the algorithms we want to run, and we have hardware implementations on the bottom. But in the middle, it's still a lot of work and development and research that is going into how these are going to be connected. And so it's going to take people like us in this call today to work on that problem. And so you might notice that the rightmost column, quantum computers today, look a lot like how classical computers, at least at a high level, were in the earliest stages in the 1950s. So we expect this development to happen in the coming decades. And notice that just like how classical computers are used by people all over the world, and you don't have to know all the details of how a computer works in order to use it. Quantum computers, it's predicted to also have this property. So not everyone will have to know all the details of quantum hardware or quantum software and all these things to be able to use a quantum computer in the future. To answer the question of what does a quantum computer look like, that's actually there's actually many different proposals and implementations and experiments people are doing to build quantum computers. So the types of systems that could be used for quantum computing that are being explored, many of them are shown on this slide. It's just pretty. So what you basically need on an abstract level is a qubit, and Alberto will shortly explain what is a qubit. But as for what is a qubit on hardware, it could be many, because it is just 2 levels quantum states that you can do operations on, then these are many examples of systems people are looking into. On the top middle, we'll focus on during this hackathon, because this is Qiskit hackathon, and Qiskit, IBM Qiskit lets you run Qiskit on hardware. So with Qiskit, you can run on both superconducting quantum hardware and trapped ion quantum hardware. And IBM researches and lets you run on their superconducting devices. Their devices, in 2019, they had about 27 qubits. And the number of qubits that they are aiming for in their future years upcoming increases as like exponentially over time. So we think that now we are in 2021. There's a paradigm shift from programming quantum circuits, which is as if you were programming gates on zeros and ones for qubit case. They're introducing something called Qiskit runtime this year, which they launched earlier this year. And so this is an applications level software library from Qiskit. We also have Qiskit application modules that emerge. So these are algorithms and libraries for the earliest applications that they envision, which are simulating in natural sciences, optimization problems, optimizing finance, and quantum machine learning. And to get an idea of quantum adventures in just industry worldwide, here's a lot of companies on one page. So I think this is a promising sign because of so many companies and countries and places are investing in quantum. Then there will be a demand for a quantum workforce, so people trained in the skills needed to build and use quantum computers are going to be a segment of the workforce and economies in the future. And now I turn over to Alberto to talk about what is a qubit.
Thanks a lot, Lia. Well, continue with this presentation. I will try to explain the basic things about quantum computing or the basic concepts. And in the next day, we can do the same presentation in Spanish. If anyone has one question or you have any interesting idea that you don't understand in English, we can talk more in Spanish tomorrow. Well, continue with this slide. We know about classical bit, or we remember what is the classical bit. We know two states, 0 or 1, or let off or let on. So we know in classical, well, we call it now the computer I'm working now in today. We call it classical computing. That means we know, well, in classical computing we know the state in every moment. We know is on or off, is working or not. Our computer or electric disposite like a smartphone, Apple Watch, or whatever you think. Well, in quantum computing is so different because we had three different options. We can state the 0 value, the 1 value, or the linear combination of two both states. We can use this with an analogy with a bit, well, with a coin, the quantum bit, because we can flip the coin. In the moment when it is in the air, we can has in the rotation moment, well, in the coin is 0 1 0 1 0 1 0 1 0 1 0 1, depends in the table or the ground or the floor and what situation you flip the coin, and the moment is stop in the, I will say, in the desk, you can see is 0 or 1. That is similar technology with the quantum computing because you can see the operation, but in the last moment, when it's stopped in the test, we can see the final state. So depends of the number of the measurement, we can see what is the probability of 10 0 or 1 value. So this is the general idea with the qubits or quantum bit. Next. But we are talking about the hardware we can work in or represent it or reproduce a quantum bit. But what is the theoretical part? We can see the qubit is in a unitary sphere. We can call in this sphere like a block sphere. This, well, the qubit is the vector, is the error. We can move it in the block sphere, and depends of this we can see a certain probability. But we can how we can obtain this probability? Well, we know in the left up part, see the equation C get this symbol. Well, this notation is about Hilbert space. This is the C state, and we can see a linear combination. We know two states, 0 and 1, like in classical way, but in 0 and 1 represent vectors to dimension 2 by 1. And this is a linear combination. You can see in the middle of the presentation, in the left part, the state 0, and the red part, the state 1. And how we can see what is probability 0 or 1 state? Well, the complex value alpha and beta, we can apply this operation to apply the absolute value and to apply the power of 2 of each scalar value, and the sum of this one is equal to 1. So we can obtain repeat values, we can repeat same probabilities, but in different position in the block sphere. That is the nice things of this qubit, because we can have infinite values, obtain the similar probability like and a half in 0 and a half in 1, because we can rotate in all the sphere the same qubit, or in this case the arrow, the purple arrow in the block sphere. And the other thing is, in classical computing, we only when we try to work with with 2 or 3 or more qubits, we using concatenated value. We can for a word, a byte, gigabytes, whatever you think. But in this case, it's different. We need to work with one certain specific operation. It's the tensor product. So with this, we can mix the linear combination of 2 or more different qubits, like in the right part, and we can work with a different state. In this case, we had state 1 and state 2, but now we have the combination of these two states, 1, 2. The next one, yeah. And well, what is the difference with the classical computer? Well, if you work with 2 qubits, you can obtain the fourth state in classical bits. If you work with 10 qubits, you can obtain 1024 classical bits states. So it's the powerful of this when you work with qubits with respect to the classical bit. How we can modify the values in the qubit is equal with like in classical way. Well, in classical we work with logical gates, in quantum computing with quantum gates. But the difference of the quantum gates is it's a matrix. All is working with matrix operator. The characteristic of the matrix is the sign n by n, and it's a unitary matrix. It's a Hermitian. That means is the inverse of this matrix is the sign of the transpose conjugate, and we apply this well, originally with the complex matrix is equal to the identity matrix. The identity, remember, is equals the one in the classical value. When you multiply one for other thing, is the other thing. And well, we remember the probability always of the scalar values in the qubit is almost 1, because it's probability. Always we need to apply the absolute value, and after that the square of, not power of the 2. And the next one, Leah. And like a classical computing, we had a basic quantum gates. The most important or representative is the NOT gate or the public X gate. Well, we had 3 basic public gates, X, Y, and Z. But the most representative is X, because it's similar to the classical NOT gate. That's mean we can represent it the light cat like the state 0, and the dead cat like 0, 1. So if you apply the state 0 the NOT gate, we can obtain the dead cat, or that's mean if you have the happy or light cat and you apply the X gate, you obtain the dead cat. If you apply for the dead cat the X gate, you obtain a light cat. So it's similar, you inverse the station 0 to 1 and 1 to 0. But the before slide, yeah, exactly. And the Hadamard gate is it's interesting because we can obtain the linear combination of the two pot state, the light and dead cat, because with this characteristic we had the linear combination of these two state. The interesting thing is you apply the absolute value and after that apply the power of the 2 of the each scalar value. Each scalar value is 1 over square root of the 2. So obtain the probability is 0.5 and 0.5. The summatory of these two values is equal to 1. So it's correct. It's possible in quantum computing work with a parallel two-state or linear combination in linear algebra. And that's one. Yeah. And how we can uh, understand the expect value when we try to work with one or more qubits is like to apply the thing to say. In this case, is obviously we can eliminate the square root of each scalar value is the summatory is equal to 1 because in the left part is 1 over 3 and the other one is 2 over 3. So the summatory of this one is 1. So applied to the absolute value and power of the 2 is 1 over 3 and 2 over 3. Well, the first one is for cat light and the other for the dead cat. And how try to work with two or more qubits is you have one qubit. The state 0 is the left part and the state 2 is the right part in the first left slide. And when we apply the matrix product is try to multiply each value of one, well, the state 1 multiplied for each value of the state 0. That's in the middle. And the result we can obtain in the right part is a vector for size 4 by 1 is 0, 1, 0, 0. That represented the two qubits. And we were working now with 4 possible quantum states. If you have three states, you have the possibility to work with 8 state and 16 and so on. The next one. You can explain this, Lia, or continue?
Yeah, I think you got this.
Okay. Okay. In quantum computing exists an interesting property, is quantum entanglement. This happens when you apply to what we call in like in classical cryptography, you had the Alice cat in this case and bot cat try to communicate it. But what happened if you apply the Alice cat, the Hadamard gate is this, if you remember, is obtain the linear combination with the same probability of state 0 or state 1 in Alice cat. But it is another special quantum gate. This is control gate. Is there is working when you modify two or three or more qubits. In this case, we had the CNOT gate. The CNOT gate is when Alice cat is in the state 1, this modified the state of the bot with the negation gate or X gate. So with the Hadamard gate, we had the half probability of obtain a 0 state or 1 state. So a half probability modified the botcat and the other don't do it. So interested is we can apply an interested state. It's calling Bell state. This is interesting because you can't separate the Alice cat and the bot cat after this operation because it's only now it's a mixed combination of these two states, and you can in a theoretical way or experimental way separate these two qubits. And now we calling like the symbol is a bell for the cat because we don't know what is is Alice or what. Only we know is now is a mixed combination of these two qubits. Now I'm talking about, well, Lia talking about the general idea or companies about quantum computing, but it is different companies that they try to explore different technologies than, well, Lia talking about superconduction is in the left part. This is working like Rigetti and IBM. In the middle part is another computer gate is, and the bottom part is Xanadu. It's a photonic. Try to with photonics try to represent quantum states at quantum qubits and try to modify it with a certain mirrors. And the D-Wave is another quantum computer. Well, let's not say the quantum computer, but this the characteristics of this quantum computer is try to optimize different problems. And IonQ and Google and like Amazon bracket is working with IonQ is another popular in this year about quantum computing. Uh, yeah, try to modify the quantum computer. Q. And exist different frameworks like we are working in this hackathon in this event about Qiskit from IBM. This is important because you can work with quantum circuits. The quantum circuits is in the center of this slide. You can apply intelligent party qubits, and depends on your interesting modification, you apply certain quantum gates like XY, C0, a certain measurement. The measurement is the output of your interested way. You can obtain in the output a dictionary or a plot about or like a histogram about your results. But it's in another interesting part, like Stanberry Fields is the framework for a photonic quantum computer game from Xanadu. And the same company, Xanadu, modify or realize an ecosystem like calling names Pennyland. The Pennyland is working with different frameworks like Qiskit Circle or different quantum computing like Yeti or IonQ or different backends like NumPy, TensorFlow, or PyTorch. The function for this Pennyland is try to design different quantum machine learning algorithms. And exists different quantum language programming like Kushar or Silku. Kushar is from Microsoft. It's the similar syntaxes for C Sharp, but you had another properties like qubit, quantum gate, and you only measure 0 or 1. So in these two different languages, you can see in the bottom part, in the center bottom part, an example for the SQL notation. AUC is different, but you have the property of obtain a certain measurement or characteristic like a classical, well, a quantum computing theory proposal. And well, how do you work with quantum computing? You can design different quantum algorithms. And well, for this first example, we can remember a classical algorithm. Try to find a repeat numbers in an integer list. So we can see the array is 1, 2, 3, 6, 29, 30, 3, and 4. If you see the repeat number is the number 3. So when a quantum computer using a specific algorithm, the Grover's algorithm, this can find the repeat number in a quantum computer when a complexity time in the square root of the n is faster compared with the classical way. The best classical way is the complexity n. So the quantum computer, we can do it and we can obtain a result faster with less qubits. In this case, we obtain only work with around 15 qubits. So the question is, with 15 bits, can we do the same solution or with the same complexity with a classical computer? That is the idea. We can obtain a faster calculation with quantum computing. The next slide. And another characteristic of quantum computing is the same quantum machine learning. We can do it this like the nearless neighbor. In this case, we can do it. Basic hello world for quantum computing is the Iris dataset. We can working with this. They compare what is the with a QRAM or quantum random access memory. This the characteristic of this is has the complexity of log n in space, and the complexity time is square over 2. So we can obtain a accuracy of approximately 82 for accuracy, because we have the correct values in the Setosa. 47 with respect 50 is the total, and the versicolor we obtain 36 with respect 50, and Virginica 37 with respect 50. So only approximately the 17 we had the ground value. So we're working with this 12 qubits. So another question, with 12 classical bits, we can design a classical and nearest neighbor is the difference. The next one, and the other way is try to use a quantum neural networks. We can work only with 4 qubits and try to map in the image to mapping a quantum state. And with only 4 qubits, we have the classification of a binary image in 3 or 6, and we had accuracy of around 91%.
Thanks, Alberto, for showing how to what is a qubit and what are quantum gates that are commonly used for qubits and some applications. What we will do next is to play around with IBM Quantum Experience. So this is a drag and drop in-browser website in which anyone can make an account for free. And also for free, you can run your quantum program on quantum computers around the world. So I'll first open this to show you what it looks like. So you can make an account. I'm already signed in, and if you go to Composer, what you can do is create a new file, and it'll look like this with you'll say Untitled Circuit, so you can give it a name. I'll call this like this one. And so what Alberto explained earlier is that each line here represents 1 qubit, and you can draw a circuit in this way. And so every qubit starts off in, by default, the 0 state. This is a measurement. So if you measure to this, it'll tell you, you'll see on the right-hand side, it generates code as you drag and drop. You can also open in Quantum Lab or write the code here yourself that you want. What this does is measure the first qubit, so which is, since it starts at 0, this is the middle qubit, and send it to the classical register 1. So this is a C3 is a classical register of size 3 bits inside. And if we do this again, but for the 2 state, then we will measure all 3 qubits at once. So far, we have done no computation. So if you scroll down, oops. Yeah, so if you look down here, you could see that, maybe we'll drag this up. You can see that it shows you that the probability of your circuits measuring of each measurement outcome, so you have 3 bits, so each bit can be either 0 or 1, but the probability theoretically is that you'll see 0, 0, 0, so 0 measured for all 3 bits, and you won't see any of the bits being 1. And this is because the qubits were initialized to the 0 state, and we did not do anything with them. So far we have not done any quantum computing, but this is to show you the quantum composer. If you look down here, it's the Q-sphere. So a Q-sphere is what Alberto described as the block sphere earlier. And so you can see that if all 3 qubits are in the 0 state, then the vector is on the sphere as 0. So pointing up. Down to the left, you also see a phase. So how IBM does it is that sometimes there's a phase involved for this state, and it will color this differently depending on what phase it is. And the phase map is shown here. But so far it is in the 0 phase, so it's purple. Something we can play around with is to see what happens if you have just 1 qubit for now. So the 1 qubit gate that Alberto showed earlier, this is the X gate. The Qiskit just uses this symbol for it. And if you notice, when I did that, when I dragged this X gate here, so let me delete it to show you again. This was 100% probability of the qubit starting off in state 0 being measured to be state 0. If you add a NOT gate here, then the qubit that was in state 0, because of this gate, is going to become a 1. And when you measure, it's going to give you the 1 result instead with 100% probability. So something you can do with the Hadamard gate that Alberto showed, I think this is broken. But anyway, if this was not broken, the Hadamard gate would show you that there is equal probability of 0 and 1 when you drag in the Hadamard gate. I don't know why it's broken, but anyway, and you can add more qubits like this, and you can do other gates. So we can do the C0 gate that Alberto showed, which is this one. And so these ones, what the C0 gate does is it's basically the quantum gate version of a if-then statement. So if the control qubit, the top qubit, is a 0, then the bottom qubit will have a not operation applied to it. It will have nothing applied to it. So it'll be identity. So if the control qubit here is 0, then the target qubit, which started off as 0, will stay as 0. If the control qubit is a 0 and the target qubit was a 1, then the C0 gate will make the target qubit unchanged. So it's as if if we deleted this would be, the probability would be the same. And if we had instead, if we just add a X gate here, then this qubit, the bottom target qubit, which starts off in the 1 state, this thing will be flipped. So it starts off in the 1 state, but because of this gate, because this is the 1 state, it's going to be the 0 state. The 0 state will flip between the 1 state. So this will be 1, 1. And finally, if the top qubit is the 1 state and the bottom qubit is also the 1 state, then the output will be 1, 0. Will be the top qubit being 1 and the bottom qubit being 0. So this is read from, this is right to left. This is the top one. This is the bottom one. So the top qubit is still 1, but the bottom qubit, which started off as 1, is now, due to this C0 gate, is now 0. So those are things that you can do in IBM Quantum Composer. You can further open it up in IBM Quantum Labs. If you click that button, you will start a server, and then you can, well, wait a bit for it. So it's loading, but oh, it's there. So this is the IBM Quantum Lab. As we saw earlier, you can drag and drop gates, and it will show your code on the right-hand side. Now that code that was earlier on the right-hand side, you can also just program directly. And this lets you do way more things than if you just were dragging and dropping gates. So this is the circuit from earlier with X gate on the control, X gate on the target, and a C0 gate. We can add more gates, we can measure differently. So if we wanted to do another C0 gate, we could just type it in like this, and then that will, and two C0 gates cancel, so that would just be identity, this kind of thing. So these, on the left-hand side, feel free to explore these free tutorials that Qiskit provides. So if you go into Qiskit tutorials, I'll show you these different folders of the different applications. And on the top folder is also the intro to Qiskit circuits and algorithms tutorials. A good place to start, well, it's a start here. So start here is a good place to start. It also tells you about the different tutorials that are there. So these ones, circuit basics, plotting data, those top ones are a good place to start. And they can get more advanced. So I highly recommend that. If you have questions while you are working through any of these, please do not hesitate to ask any of the mentors that are here at the hackathon. We're here to help. now I can show an application of using the quantum gates. So far we played around with the qubits, the gates, and now we want to show a quantum circuit. So this, as a review, Alberto went over quantum entanglement, which is when you have two qubits. This qubits, the happy cat here, or alive cat, represents the qubit 0 states, and then the quantum, like the dead cat, represents the qubit 1 state. So in this circuit, what this means is if you have start off with 2 0 states, and then you apply first a Hadamard gate on the top, an Alice qubit on top, then a C0 gate here, where Alice's cat qubit represents the if, the target, and then Bob's qubit represents the then, or the Alice's represents the control and Bob's represents the target. Then you'll have this Bell state. This is the maximally entangled state there is for 2 qubits, because either both qubits are in the 0 state or both qubits are in the 1 state. And if you measure, in other words, if you measure one of the qubits, then you'll know the results. You'll know what the state of the other qubit is, because they have to be the same. They have to be both 0 or both 1 if you measure them in the 0-1 basis. Something that you can do to compute this, there's different ways in which you could figure out what this circuit is doing, other than if you were to program it and run it in Qiskit, run it in a program, like run it on a simulator or on hardware. So as you can see, this matrices here, this matrix is the Hadamard gate matrix on the top left, and then this matrix over here on the right is the C0 gate matrix. And if you wanted to compute what this is, you could just start with the qubit 0 state matrix, which is just a vector of length 2, where the top element of that vector is 1 and the bottom element is 0. And if you multiply the matrices in order, so from left to right in the circuit model means you're multiplying the matrices with the leftmost thing on the right. Then this wire with nothing on it is the identity matrix, which is just the 2x2 identity matrix. And by multiplying in this way, you can compute exactly what the state is at the end, and you will get this Bell state. My research at Oxford involves how to do this type of computation using diagrams. One reason why this is useful is because if you have n qubits, then your matrix is size 2 to the n by 2 to the n, because there's 2 to the n combinations of 0 and 1 bit strings out of length n. To go over this circuit for quantum teleportation as an example, here on the top is you have a generic state psi, and then here on the middle you have the 0 state. And these top above this dash line, these are Alice's states, whereas on the bottom you have Bob's state. This is called quantum teleportation because if Alice and Bob share a Bell state, so this thing over here where my cursor is, this is the Bell state from the previous slide, this thing. If they already shared a Bell state, you can then perform a C0 gate, an H gate then here, and 2 measurements here. So this thing together is called a Bell measurement, and you'll see that because it is as if you did the Bell state but backwards. And if you do this, then you can teleport the value of psi, which is Alice's state here, to Bob, even though you're not directly sending anything from Alice to Bob. So in time, it could be as if Alice is sending information back in time and then forward to Bob, because the only entanglement, so information between Alice and Bob, was this part at the beginning right here. And also this classical arrow, this purple arrows here, represent that based off the results of this measurement, Alice can send that information what the measurement result was to Bob, and then Bob can perform the corrections accordingly. Since there's 4 measurement results, Bob doesn't know what Alice's state is until Bob knows which of the 4 possible combinations of corrections to perform. But these purple arrows are drawn in purple. They're not part of the quantum circuit, because they are classical information. Basically, just which of the 4 possibilities was it? Whether Alice measured 0 and 0, 0 and 1, 1 and 0, or 1 and 1. What the corrections are specifically is that if Alice measured a 0 here, then Bob should perform a Z gate here. So this is also called the CZ gate, because it's the if this is 1, then perform this gate on the target, where this gate is the Z gate, which is it's the same thing as the X gate, except it's about the Z axis rather than the X axis of the block sphere, where you can represent the state of any qubit on the block sphere. And whereas on the middle qubit, if Alice measures a 0, then Bob does not need to perform the correction. If Alice measures this correction of X gate, if Alice measures a 1 here on the middle qubit, then Bob needs to perform an X operation here to correct. So we want to see what this is like running on a quantum computer. Here's what the circuit from the previous, so from this slide here, this circuit, if you were to run it here, it looks like this. So this is the IBM Quantum jobs, so maybe that's the right way. So what you can do is, when you are in the Qiskit Quantum Composer, something you can do is click on, here, let me just show it. So if you go back to the IBM Quantum Composer, and you can do this with labs too, if you have an account, which is free, you can click here on the top right, Setup and Run, and I'll show you here, choose a system or simulator, and you can see and scroll down all these bunch of them, and you can also choose here to see the different types. So these simulators are simulating, and so they're perfect, assuming so they don't have error unless you intentionally choose to simulate the error. But real quantum systems have a lot of error, so as you will see, it's they have a lot of error. So it's predicted that as error of these real hardware goes down over time, we're going to have some future era that's called the fault-tolerant era, in which quantum computers can correct themselves, and you can do error correction procedures. But in the meantime, we still have a lot of error on the quantum computers. If you click on these, you can see that the IBM quantum systems are named after where they are physically located. So this is your task that you send is going to be sent all the way over the cloud to be performed. So what we can do, I will use this quantum teleportation circuit and have it run. So here this is the same quantum teleportation circuit as earlier, and here we're only measuring the 2 state. The simulator will still show you as if you measured every state, but in the actual hardware, if you don't measure it, it will just be 0. If you click Setup and Run, let's run on, it can run on IBM Santiago, I think. And now it says on the top left, job sent to IBM Q Santiago, and we just wait. So it says pending. And you can look at your current jobs. I can show a job that was run earlier, so I could show this one. So what this was, you can click See More Details, and if you click See More Details, it'll be this one. This was that circuit. Here is the original circuit that you put in the composer. But in order to optimize and also make sure that the circuit can be run on the actual hardware, Here is a transpiled circuit. So for example, the connectivity of the hardware might not be what it is, what might not allow direction gates that you can do in any direction. And you can see the results here, although in simulation it was supposed to be that this had 100% probability of being 0, this bit being 0, and 0% being of this being 1. But due to there being a lot of error on this device, it's actually like pretty 70-something% error. And so you get a significant probability of the wrong answer. So it requires both hardware and software advances to make this much more robust. So far what we have seen actually is the CHASM quantum assembly language that is generated when you drag and drop these. But there's actually the Qiskit programming language where you can do the same thing, but do more operations. And because it's has more features as a programming language, you can be more expressive when coding. That concludes the composer part of this workshop. That also close to concludes the whole workshop, and so thank you for joining. We will take any questions that you have for the next few minutes. I believe there's also a workshop right after this one.
¿Alguna pregunta, ya sea en español? Sí. Aida, ¿quieres hablar? Puedes abrir tu micrófono.
Sí, muchas gracias. Bueno, first, it's a pleasure to meet all of the presenters. Thanks for the opportunity. Second, I don't know if this question is, I don't know if I should really ask it, but it's more about the mathematical background needed for like entering this in quantum computing. So like aside from the like computer science aspect and electronics and physics, so like is there something else I should study for? It's specifically like purely mathematics, or that's like my question. I don't know if I formulated it very well. So
that's a good question. Thank you for it. So actually something we didn't touch as much upon is that quantum computing is a very interdisciplinary field. And so there's lots of open problems and challenges that all across all the different fields. So many fields that people working in quantum computing are from include computer science, physics, material science, chemistry, finance, biology, like a lot of different applications of quantum computing are all involved. So I don't think you could get people to agree on what is the best place to start there's not a single way to learn quantum computing. So actually these concepts, they have many different ways that you can learn it. For example, in this presentation, we gave the approach of using vectors and matrices. This is also the approach used by the Qubit course, which is by the Coding School nonprofit. They run this year-long course targeting high school students. So they teach high school students matrices and complex numbers, and that's how they can learn what quantum computing, how quantum computing works. I was a teaching assistant for them for a semester last year and really enjoyed it. Another approach that I mentioned was that there's a textbook on how to use quantum computing using diagrams. So this one is more college level, but they are also making the same textbook, but for high school level. That's not out yet. So these diagrams are called the ZX calculus, and the textbook for undergrad or and above is called Picturing Quantum Processes. That's a good textbook. So sometimes a lot of ways people start out is with the physics. So bracket notation we also went over in this presentation. That's these where you have a straight line here and then a right angle bracket here. That's called a ket. And if you have the same thing but flipped horizontally, so if you have the left angle bracket and a straight line, that's called a bra. And a bracket is just their inner product. And so this is also called Dirac notation because it was invented by the physicist Dirac. And so you can use that notation instead of matrices to be more compact. So that's also something good to learn. If you're interested in quantum programming, I mentioned the Qiskit tutorials. There's also tutorials for other quantum programming languages as well, and many resources online. Qiskit has a YouTube channel. There's lots of blog posts, and hackathons like this are probably the best way to gain experience to practice the programming. There's also many good textbooks out there. There's also, if you want to get a sense of the projects that other people have done, our blog is one place that goes through quite a few examples of quantum programming and quantum learning projects that people have done, quantum games. So, for example, there's going to be a quantum games workshop this week about how you can learn and create games to teach people quantum concepts. I hope that was a helpful answer. As for more resources for beginners, I highly recommend checking out the other workshops that are this week and the hackathon, because we'll have mentors on hand to help you if you have any issues or just answer your questions to help you learn.
Yeah,
all right. Thanks for your answer. That's all. Thanks.
Thanks. We had other two questions, Lia. Is from Gabriel. Can you tell us some results for beginners?
Okay. In addition to the ones I just mentioned, it's good to see if there's courses that are in your area or online or in the interests that you have. So, for example, there's a QWorld which offers courses and certificate programs. So if you go to their website, they're a nonprofit and they have all these events and quantum summer schools, different certificate programs in different areas. So you can find the one in your local area. There's also, there's also what I mentioned, the coding schools, Qubit by Qubit course, which run these courses. The course was free for the entire year, which is a really long course. And you can see their programs. They have scholarships even though their courses are no longer free, but they're by a nonprofit. So this is to fund the paying of the course instructors. And there's also a lot of events by IBM. So IBM has a lot of if you go to the Qiskit Slack, they're going to advertise all their events throughout the year. This will just take you to my login of the Qiskit Slack, but you can see the IBM Qiskit website. They have a Qiskit open source textbook. So they're making a lot of educational material. It's open source, so anyone can contribute and make pull requests, make recommendations for the IBM Qiskit textbook and the Qiskit programming language itself, which is also open source. So this is the most popular quantum programming language and a good place to start. And the people on Qiskit Slack are very helpful to help if you have any questions using the language. There's also, so Alberto and I are both Qiskit advocates, and others in here as well who can answer questions about getting started with Qiskit. I see another question in chat. It is from Eric. It says, I have a question. It is always necessary a physical system or problem that has two possible states, at least for implementing quantum computing, right? For example, right and left or up and down, etc. So this question is the topic of my PhD research is you don't actually you're not restricted to just two states in a quantum computer, in a qubit. So classically, in your computers today, you only have 0 or 1. People always program in that because the hardware and devices have been developed because it's a classical value. You have either 0 or 1. For example, their bit is like some voltage level. And if the voltage is above a certain threshold or below a threshold, then that bit is either 0 or 1. So if they wanted to make more possibilities, so more than just 0 or 1, they can make 0 or 1 or 2 or continuous values. Then it would be very hard to design because they would have to start from the very beginning and everything that builds on top of it, the higher layers, device layers of the computer and the applications will have to change. But for quantum computers, the higher level systems, so it's just a lot of these quantum hardwares, not all of them, but many of them, how they work is they have this energy potential and it's a nonlinear oscillator. So it's nonlinear because these spacings of these energy levels are not equally spaced. And so the next higher energy levels are all just there already, and they're part of the device, and you can already program them. So in the recent years, IBM Quantum made their Pulse module open source, so you can directly program the pulses so this is below the gate level, the pulses, microwave pulses that are what's actually being sent to the device. And being able to control the devices and open source that on the pulse level means that you can, for example, use the 2-level state in addition to just 0 and 1 of each qubit. So that would be called a Q-trait, where there's 0, 1, and 2. And a Q-dit is when you have D levels for any D. D can be 2, 3, 4, 5, etc. All the as many as you want. In practice, many hardware and software don't support beyond bits so far, just qubits. But so I hope that answers the question. But basically, there's very interesting physics and very math and computer science that gets involved if you have more than just 2 possible states per qubit. But we can talk more about this after if you would like. I am in the Discord of the hackathon.